guys, welcome again. It's Miss Nicole. Today we're going to be talking about the limit definition of a derivative for the AP Calc Prep tutorials. So let's begin. So first, the definition of a derivative in regards to limits is the limit as the change in x approaches 0 of f at x plus the change of x minus f at x over the change in x. Traditionally, you will see this in class as the limit as h approaches 0 for f at x plus h minus f at x over h. Now, what does that actually mean? Let's talk about what does the change in x mean, right? So we have that delta over here. That just says change in x. So for example, if we're starting at this point in time where x is equal to, say, 0, right? So this would be the negatives, this is positive, and over here we end at 4. So our original value is x is equal to 0. Our secondary value is going to be x is equal to 4. So the change in x is going to be x1 minus x naught, which is 4 minus 0, or 4. Okay, so that's the change in x. So when we're talking about limits and we're looking as the change in x approaches 0, we're actually looking what happens as the distance between these 2 points, the distance, right, the change in x, gets closer and closer to 0. Okay, so what happens as there's less space between them? So for example, if your friend and you are some distance apart, say 10 kilometers away from one another, you guys decide to meet somewhere, and then when you guys meet at the meeting point, the distance between you two is 0. Okay, so what we're saying is what happens to the function as the distance between 2 points ultimately becomes 0. Now, like I said, traditionally you will see this instead of change of x, you will see as a value of h approaches 0. They both mean the exact same thing. A function is differentiable, meaning it can be differentiated using this limit at any x for which the limit exists. Okay, so we're talking about limits again. So let's remind ourselves that the limit exists if and only if we have the left-hand side limit exists, such that, let's say, f at a is going to be equal to some value a. The right-hand side limit exists. F at b is equal to some value b, again using the limit definition that we just did above. And finally, if the left-hand side equal the right-hand side. So to simplify this further is if we take two limits of two different sides coming from the positive and the negative value, they need to equal to one another. And we're going to do an example later on. Another term you're going to see a lot in this unit is going to be the average rate of change, and I'm going to be writing ROC in short, as well as the instantaneous rate of change. So the average rate of change for a derivative over here that we're talking about is simply going to be this fraction, okay? And this is called a difference quotient. So if you were to plug in for some a value, again, we're saying the derivative at some point is going to be, at some point a is going to be the limit as h approaches 0 of f at a plus h minus f at a over h. And you would just plug in the values in here, and then you would get the average rate of change. And we're going to look at this geometrically in a second as well. Just make sure you notice it is the secant line. The instantaneous rate of change is going to be the limit as you would take it above at some point a. So the instantaneous rate of change is simply the derivative at some particular point. So I know this is a little difficult right now to understand, but once we dive into it, I hope these definitions will clear up as we go. So let's see what this looks like geometrically. So say we have some sort of function f at x, okay, and 2 points that we selected, p and q. Let's label these values. We start by p over here. So we have, remember, we need to have an x and a y-axis as well. So on the x-axis, we have some sort of value a over here that corresponds. Q is going to correspond to a plus h. Therefore, over here we have f at a, and this is f at a plus h. Now let's simplify actually what this means. Okay, so these are just some values over here. So let's say on the x-axis we have 2, and this value over here is 4. Well, what's the h value? Well, we're saying h is going to be the change by how much a increased or has decreased to get to this value here. Okay, well, we know that's going to be plus 2. So our h value is 2. That's why when we're drawing this geometrically, we labeled this difference over here by h. Okay? So let's see what this looks like now. We have a secant line that we can draw through the points P to Q. Like so. Okay? Recall that a secant line passes the function at 2 points. Okay? So it has to pass the function at 2 points. So basically we're saying from point here, which is a at f at a, notice that this is the x value, this is the y value, and then a plus h and f at a plus h. Again, x value, y value, we're just labeling simple coordinates in the form of x comma y. So the average rate of change is actually going to be the line connecting these 2 points. So as I mentioned before, the average rate of change is simply going to be this fraction over here, right? The quotient difference. So f at a plus h minus f at a all over h. Okay, well, let's really see what that actually means, okay? Well, I told you it's actually going to be the secant line for the average rate of change, but what about it? Well, we're going to be using the slope, and if you recall, the slope formula is going to be y2 minus y1 over x2 minus x1. So let's plug in those values based on the two that we have here, right? P and Q. Both of those points are on the secant line. Therefore, we can use them to determine the slope of the secant line, the one in red. So let's start with, we have f at a plus h minus f at a all over a plus h minus a. And we notice over here that the two a's cancel out. And all that we're left with is f at a plus h minus f at a all over h. So later on, when you're going to be asked for the average rate of change, you need to remember that it's simply going to be the slope of the secant line. That's the easiest way to remember that. We're looking to see overall what is going to be the slope at every single point on this graph. That's in simple terms, that's what the derivative actually means, right? It's going to be the slope of the tangent line at every single point in time on this graph. So what did I just say and what does that mean? Well, when we're taking the derivative at some particular point, say just simply P at A, we're actually determining the slope of the secant of the tangent line at that value, like so. Remember that tangent line passes the graph only once. So the tangent line just represents the derivative at a particular point, which means f prime at A. And f prime is the way we note what a derivative is, if we're going to scroll up above and just remind ourselves of that. Okay. So I think that will be all for today. I'll see you in the next class where we'll be talking about derivative formulas and rules.